All right, guys. So, I know in class today we finished the majority of the first part of inverse function notes. Okay. We kind of ended around here. All right. So, ideally, when you think about it, what do inverses do, right? You saw this in the Desmos. If you plug a number into a function, it generally will output a different number, right? Think of the function machine from elementary school. So for example, if we plug in x equals 2 into the function f of x, you will get 5. Now, what inverse does is if we plug in the answer, which is 5, into the inverse function of this, the answer should be 2. This is because an inverse function essentially will undo a function. So if we plug x into a function and then plug the output into the inverse, which is the y, into the inverse, we should end up with x again. Okay, so let's put that to the test. So two functions, f of x and g of x, are inverses of each other if and only if, so this is the proof. If f of g of x is equal to x, and the other way around, g of f of x is equal to x. To show that two functions are inverses of each other, we must show that the inverse of the function and the function of the inverse both equal x. So if we want to determine if two functions are actually inverses of each other, we need to check both. Which brings us to example 6. Let f of x and g of x be the functions below. So here's f of x, here's g of x. We want to see if f of x and g of x are inverses. So when they say determine if they are inverses of each other, we basically have to see that is f of g of x and g of f of x, they both must equal x. And if they are, then that means that this guy right here is an inverse of x, of f, sorry, and this one is an inverse of g. So how do we check that? You basically just follow what they're telling you to do. So we plug in the 2. So in here, we're gonna take the g of x, plug it in. And now we're gonna take this part, half x plus 3 halves, and we're gonna plug it in for x in f. So 2, and instead of this x, we're gonna put parentheses and put in our input function plus 3 halves. Now just simplify it. If we end up with x, we have to check the other way around. And if we don't, then automatically we can say these are not inverses of each other. So when we simplify, first we got to distribute that 2. So 2 times 1/2 is going to be 1x. 2 times 3 halves is going to be 3 plus 3 halves. Okay, I don't know why I put a plus here. I just noticed that it's supposed to be minus. My eraser's too big. It's fine. So let's do this again. All right, so we got 2, my plus 3, 2x. No, what's wrong with me? My God. So we got 2 times half x is 1x. 2 times 3 halves is going to be plus 3. And then, of course, this minus 3. So you notice that these two will cancel out and you're left with just x. So far, it looks like these two are going to be inverses of each other, but we have to check the other way around as well. So now g is going to be on the outside and f of x is going to be on the inside. So now we're going to plug in 2x minus 3 into g. So where there was an x, we're going to plug in our 2x minus 3. And now we do the math. So distribute the 1/2 first. So 1/2 times 2 is going to be x. 1/2 times negative 3 is going to be minus 3/2 plus 3/2. And you notice that these two will cancel out and you're left with x. So because the composition of both of these functions give us x as the output, right? That means these two are inverses of each other. Note, sometimes we must use a restricted domain to ensure that two functions are inverses. Like we saw with quadratics, right? The only way that this guy can actually be a function, an inverse function of h, is if we restrict its domain. So show that h of x and k of x below are inverses anytime x is going to be greater than or equal to 10. So knowing this and seeing this function right here, this radical, greater than or equal to 10 means that we're going to be restricting the inverse function. So the domain of this guy has to be greater than or equal to 10, because if it was less than 10, you would end up with a negative number and therefore an imaginary number in there, okay? So how do we check? We have to check 2 things. Step 1, we gotta make sure that h of k of x is equal to x. And then next, we wanna make sure that k of h of x is also equal to x. So let's do this guy first. So we're gonna plug in k, which is square root of x minus 10, into h. So now parentheses squared plus 10. We're going to plug in here square root of x minus 10. So obviously square rooting a square, squaring a square root, right? Will get rid of the square root and the squared. And then we are going to be left with x minus 10. But remember, because this was in a square root, we have to remind ourselves that this guy has to be positive always, or else this whole thing is just not going to work. Okay? Now, the reason why it's important to put these absolute values is to remind ourselves of this restriction right here. Now, for this restriction, X has to be greater than 10 or equal to. So any number I plug in here, right? 10, 11, 12, 13, 14, and so on and so forth will always be positive. So I can kind of ignore these absolute values for this specific problem, but you do have to keep absolute values until you've identified your restriction and that it remains positive. So we got now X minus 10. I can get rid of the absolute values. The reason why is because you really can't combine these two once one is in the absolute value and the other one is not. And once we do that, the negative 10 and the positive 10 go away and you're left with X. So why did we remove the absolute values? Because of this restriction. It's always going to be positive based on our restriction. We'll do an example probably in class of when it's not. All right, K of H of X. So now we're going to take K, we're going to put H of X in here. Next up is to grab the K function, and then where there was an X, I'm going to plug in X squared plus 10. And now we can complete this problem. Remember, this guy right here, these parentheses, they're not really necessary. So just a little side work, X squared plus 10 minus 10. In here, what happens to the plus 10 and the minus 10? They cancel out. So now we're really left with just X squared. Now the square root of X squared is going to be X. And we have to remember, because it's inside of this radical, it must always be positive. Okay? This guy has to be positive. According to our restriction, X is always going to be greater than or equal to 10. So because X is greater than or equal to 10, always, I can say it's not the absolute value of X, it is actually just X, because I can plug in 10, 11, 12, and it will always be positive. So I don't need those absolute value signs. So because both compositions give us an answer of X, these two are inverses of each other. All right, last example, show that N of X and P of X below are inverses. And then of course, X cannot be 0 and X cannot be, make that arrow. X cannot be 0 and X cannot be 4, because if X is 0, then this guy is undefined. And if X is 4, then that one is undefined. Okay, so the domain on this guy, X cannot be 4. And the domain on this one, X cannot be 0. Okay, so now let's check. So the first thing we're going to do is we're going to do N of P of X. And then of course we can't forget to check P of N of X. So N of P of X is going to be N of 6 over X plus 4. Okay, we have to remember that X cannot be 0 in here. So now once we take this and plug it in to N, it's going to be 6 over, where there's an X, I'm going to put all this stuff in. So 6 over X plus 4, and then minus 4. All right, so you notice that the 4s will cancel out. So you're left with 6 over X. Flip the guy and multiply, right? So this is really going to be 6x over 6, which is just x. So far so good. Next up, let's do p of n of x. So p and then n of x is going to be in here. We got to remember x cannot be 4. So let's take this part and plug it in for p. So 6 over x minus 4 plus 4. Do a little bit of algebra, flip the guy and multiply, right? You end up with 6 times x minus 4 over 6 plus 4. The 6's cancel out, so you got x minus 4 plus 4. The 4's cancel out, and you got x. So both compositions equal x, therefore, these two are inverses of each other. Okay. All right, so that's it for 2.8 part 1. Let's finish up the notes for 2.8 part 2. All right. So if f and g are inverses of each other, then we say that g of x can be written as inverse of f of x, right? So if x and y is a point on the graph of f of x, then y and x are a point on the graph of g of x, because remember, g of x is the same thing as the inverse. With inverse functions, all of the x and y values are switched. So the graphical behaviors in terms of x and y will also be switched. For example, the domain of f will now be the range of the inverse. And then the range of f will become the domain of the inverse. All right. A continuous function will only have an inverse function if it is strictly increasing or decreasing, like a line, right? Or even, a cubic function that passes the horizontal line test everywhere, okay? If a function changes from increasing to decreasing, or vice versa, at any point, like a quadratic, like we looked at today, it will not pass the horizontal line test. And therefore, its inverse relation will not pass the vertical line test as a result. And in order to accommodate that, we will have to restrict the domain of the inverse. Okay. So let's look at first example. Before we do the first example, I kind of want to make the inverse table here really quick. So I have it because it looks like they're asking about the inverse, right? So let f be a continuous function with selected values in the table. Let g be the inverse of f such that g of x is the inverse. Find the following values. So before we do that, I'm going to make the table for g of x. Remember, g of x is the inverse of f. So when x is 6, g of x is -3. When x is 3, g of x is -2. When x is 1, this is 0. When x is -1, this is 1. When x is -3, this is 4. And when x is -7, this is 6. Now that we have both tables, let's go ahead and solve. So first one is pretty easy. F of 0, f of 0 is 1. And then f of 1 is going to be -1. Done. G of -3. Because I made my table, G of -3 is just going to be 4, right? So you have to remember that it's asking for inverse of f of -3. Now, even if you didn't make the table, you know that if it was that, how should I say? The answer of the inverse is the x, right? So even if I didn't have this table, if I knew I'm looking at the inverse, I'm going to be looking for the y value on this table. And that's going to give me 4. All right, G of 6 from the table, -3. But even if you didn't make the table, you know to just look at the y value when you're trying to figure out the inverse, because the input, right, was the output of the original function. So next up, G of -1. So -1 is 1, and then G of 1 is 0. Now, what is this saying? Remember, this is just a different way of writing the composition. So it's f inverse of f of -2. So f of -2 is 3. Now the inverse f of 3, because it's the inverse of f, we're going to be looking at the output values, and the answer is going to be -2. But remember, inverse f is really just g. But you'll get the same exact answer. Okay? Because this is just saying what is g of 3, and that's -2. All right, inverse of -3 of f is 4. Because that's the same thing as saying g of -3, which is 4. All right. Next up, we have a graph. So first one was a table evaluation. Next, we're going to do a graph evaluation. So the function k is defined over the interval from -4 to 11. Okay, -4 to 11, as shown above. Let the inverse of k represent the inverse of k. K -1 be the inverse of k. What is the minimum value of k of x? This is not the inverse. So the minimum value of k of x, that means the lowest y value. Okay, that's going to be lowest y value, -3. Okay. Now, what do you think the minimum value of the inverse of k is going to be? All right. That's going to be -4. All right. Graphically, it's going to be -4. And where did I get -4? It's basically the input that gave me -3. Okay. So do you see that? It's going to be -4. All right. So here's how we're thinking about this. This is the lowest value. I'm going to write this down as -4, -3. That is where the point of the lowest value is. Now the inverse is also going to be at this lowest value. But what is the inverse going to be? How do we give the points? It's -3, -4. And remember, whenever they're asking about minimums or maximums, they're asking you for the y value, like lowest to highest, right? So this is how we go up and down. So this is lowest to highest. And that's why the answer will be -4. All right. Find the inverse of 6. Okay. So let's remember, because this is the inverse, this is actually the y value. So all I have to do is go to the y value of 6 and identify the x from the original function. Okay, because on the original function, 11 gives us 6. So that means on the inverse, 6 will give us 11. So K inverse of 6 is going to be 11. And K inverse of 4, remember, I'm going to look at the y value. So at 4, the answer will be 6. And I can confirm because on the original function, 6 gives us an output of 4. Therefore, on the inverse of 4 will give us an output of 6. All right, next up. Same types of questions, right? Now remember, graphically, always recall, oops, let's remember that graphically, right, always an inverse is symmetrical over y equals x. And the points of the inverse will be the same at that line. And then every other point, so like this point right here, which is 4, -1, will be at -1, 4. This point, which is at 0, 5, is going to be at 5, 0. All right, another point, 8, -3 is going to be at -3, 8. -2, 7 is going to be at 7, -2. All right, not my best drawing. Yeah, but you guys this is probably too far down. All right, so the function is defined on this interval from -2 to 8. Let the inverse represent the inverse of f. So we want to figure out what is the maximum value of the inverse. So let me ask you this, what is the maximum value of the original function? The maximum value of the original function is going to be 7. So the maximum value of the inverse is going to be what gave us that 7. I just said that completely wrong. Ignore what I just said. So on this one, the maximum value of the original is going to be 7. Okay. So the maximum value of the inverse actually came from the point all the way over here, right? Because this guy got inverted. So the maximum value of the inverse is going to be 8, which is the biggest x value on the original function. Okay. All right. So next up, we want to know what is the inverse of 3. So remember, we're looking for the y value on the original function. And 3, here's y. It comes from It comes from 2. Inverse of 1. Remember, you're looking at the y value because this is the inverse. And that comes from 3. Okay. And that's basically because on the original graph, that's where the y value is 1. That's where the y value is 3. All right, so what is the domain of the inverse? So let's write this. What is the domain of the original function? They gave that to us, right? So it's -2 to 8. And the range of the original function is from -3 all the way to 7. And they're both included because they are closed circles. So just like we talked about earlier, inverses completely switch everything, even their function, what they do, right? So the domain of the original becomes the range of the inverse. And therefore the range becomes the domain of the inverse. So what is the domain of the inverse? That's going to be from -3 to 7. All right. So here's our graph of G, and then we also have a table of H. So be careful because we're talking about 2 different things. The function G is defined over the interval from -3 to 10. So from -3 to 10. Let the inverse G of -1 represent the inverse of G. And then values of increasing function H. So this is the actual function of something completely different for selected values of X. Find the following if possible. All right, first one is easy. We have no inverses to look at. We just want to do H of 6. H of 6 is 10. And then G of 10, again, no inverse, just the actual graph of G. G of 10 is going to be -1. So that's done. Next up, they want us to figure out H of 0. So just the function itself, H of 0. And that is going to be 3. Now here they want us to identify the inverse of G of 3, right? So because it's the inverse, this guy right here that we're going to be looking at on the graph, we're going to be looking for the y value to figure out the answer, which is the x value from this graph. So we're going to look at the y value of 3. And it comes from the x value of 4. All right, next up, G of 8. That's just the function itself, right? So no inverse, so just at 8, what is it? It's 0. Now, because they're asking us for the inverse of h at 0, this is going to be our y value, and our answer is going to be the x value from the table. So on the y value, where do you see a 0? Here it is. So our answer is going to be -1. And the last one, inverse of -1. So again, we're going to look at the y value of -1. That comes from 10. And then inverse of h of 10. Remember, we're looking at the y value. So that's right here. So that's going to be 6. Oh, and that's it for unit 2.8. All right, make sure you guys have these notes completed, and your homework will be on Schoology for this second part of the notes.